All right. Like I said, it's two parts. We'll do part one. We'll write a test. Then we'll do part two. We're gonna do a bunch of. Once we get into part two, we'll do more. We'll do a few titration labs. Okay, so figuring out concentrations of things. There's a lab I wanted to do in solubility that I never did, but I'll fold it into acids and bases because it's a different type of titration. A lot of titrations you use acids, but you can actually use solubility in a titration experiment to reach endpoint. So we'll talk about that later on. But the first thing we have to do is talk about what is an acid. What's an acid, people? That is the kind of high school, elementary, middle school definition of what an acid is. And it works all the way up until about this point. Okay? It's not wrong. It's not wrong. Don't get me wrong. But basically, you learned that acids are compounds that begin with an H or a hydrogen. No, we're just going to say H. Start with a hydrogen, right? You learned about HCl, H. You don't have to write these down. H2SO4, H3PO4, right? They all start with an H, so we call them acids. And bases end in OH. Classic being sodium hydroxide, calcium hydroxide. It was on the midterm. All right. So anything that ended in an OH was a base. Anything that started with an H was an acid. Okay. So now there's a couple of other definitions of acids. All right. The Arrhenius definition, and we still use this. We're going to focus on something else that we call Bronsted-Lowry later on. But an acid is any substance that produces H plus ions in water. So in water. So for example, the classic is HCl. You put into water. And you get hydrogen ions and chlorine ions. All right, let's talk about this H plus for a sec. Because when I first taught this, so I won't say H plus. I mean, I will, but what I'm going to say most of the time, and you'll see how it ties into the definition, is that's a proton. Okay, a hydrogen with its electron ripped off is a proton. Okay, because hydrogen's the only element. I hate that we don't have a periodic table at the front because I want to just be like pointing at it. It's the only element that doesn't have a neutron. Okay, so if you rip the electron off of it, right, it's just H plus, but that is a proton, right? It's usually what's in the nucleus of all the other atoms. Okay, so I'm going to say proton. You'll hear that a lot in this unit. All right, so proton is just a hydrogen atom with the electron ripped off. And I said that at first when I was first teaching this, and kids just kind of nodded. But then, like 3 classes in there, some kids like, "What's a proton?" Because I know you know what a proton is, but you think of it as part of the nucleus. All right. In acids and bases, it is this. Okay. So a proton is hydrogen atom with no electron. Ripping the electron off is why it's positively charged. Okay? So you produce protons in water. If you put some substance into water and it produces protons, that's the Arrhenius definition of an acid. What do you think the definition of a base is? Well, let's look at this. We used to say things that began with an H were acids, and things that ended with an OH were bases. So what do you think the Arrhenius definition of a base is? Basically, when you put something in water, it produces hydroxyl atoms or ions. So the classic is sodium hydroxide. You get sodium and hydroxyl groups, OH minus, and those should be aqueous. AQ. Okay. We also, in grade 11, you talked about neutralization reactions. What's a neutralization reaction? Oh, when you react an acid and a base and you produce a salt and water, right? Now the salt isn't always salt, sodium chloride, but it can be, all right? So, so why is my pen not working? So if we'll do the classic HCl plus NaOH. So we have an acid, we have a base, we react them together. It's a double replacement reaction. So the sodium bonds with the chlorine and the water bonds with the hydroxyl group to produce, or the hydrogen bonds with the hydroxyl group, and you get water, and you get quote unquote a salt, in this case NaCl, which actually is table salt, and water. Okay, so that's just a neutralization reaction. All right. Properties of acid. General, anyway. Neutralized by a base. When I say neutralized, what do I mean? Yeah, like the OH and the H will cancel each other out, right? Neutralization would be this, H and OH will produce water. Water has a pH of 7. That's neutral. Okay, so they sort of they neutralize each other. I don't recommend you do this in a lab. They have a sour taste. Probably acidic. So lemon juice, right? You drink some sort of citric acid. It has a sour taste, right? Don't drink hydrochloric acid or sulfuric. No. But also, I've never heard of a student inhaling lead sulfate either. So, and then people were telling me. I think people have a general sort of aversion to acids and bases. I think. I hope. Acid, anyway, tends to indicate danger, right? Bases, people will mistake bases. You can be burned by a base, like a really strong base. They turn litmus paper red. We will see litmus paper throughout this. Have you used litmus papers before? Litmus paper doesn't tell you anything other than the solution is acidic or the solution is basic. There's pH paper that'll tell you the pH, but we'll talk about that, and we'll use that. And you've probably done this experiment in grade 10 or something. They act on most metals, not all, to produce hydrogen gas. Reacted with zinc, I think, in grade 10. You collect the hydrogen gas, put it in a balloon, you go pop, or you put it in the test tube, go pop. Did you do that in grade 10? Yeah, that's kind of a common one. Okay. So those are some general properties of the Arrhenius acids. Arrhenius bases. All right, what do you think the first one I'm going to put is? Neutralized by an acid. They have a bitter taste. Again, bitter based, bitter taste. Again, don't try it. So baking soda. You go home and eat some baking soda if you really want to, but coffee I think is slightly acidic. You said what? What? Coffee? Put baking soda in the coffee?
No, I don't. I've heard of it.
Really? Why?
Don't ask me.
Pause the video. I have a story.
Wait, what about the people at home who want to do?
Okay, no, we're not looking now. You can look later. Okay. All right, back to this. Acids turn litmus paper red, bases turn litmus paper blue. Look at that.
How did you know about that? That's not even true though. What is true is also.
Oh, and if you were in chemistry 11 and you made soap, such as the excellent bars that are over there, you use bases. What they do is they will, if you put soap on your hands, what feeling do you have? It's like slippery, greasy, right? It's because they're sorry? One end is hydrophobic. That's how you wash it off. But one end is what am I trying to say here? Like starts to break down the fatty acids and stuff, and that's the slippery feeling. But the hydrophilic part of a soap is like one end is like will have some OH or some sort of charge. This will bond to the water. The other end's like a fatty acid, which is basically just, if you remember your organic chemistry, you can draw them like that. That sticks into the fat. Then you run water over it. The water grabs this and pulls the dirt off your hand. That's how soap works, basically. But they're slippery to the touch. Bases are slippery to the touch. Don't, when we're using base in class, pour it on your hand because you want to feel what the slippery thing is. Did he really? Seriously? Okay, well, there's the practical example of what I'm talking about. He was like just a walking experiment, wasn't he? Okay, so that's one definition. So we've gone from acids start with an H, bases end in OH, two. We have these definitions. We produce protons in water, or we produce hydroxyl groups in water. And then we have some properties of those. And then we get to the stuff that we're mostly going to focus on. The Bronsted-Lowry definition of an acid and a base. Okay? So, you will see later on in this unit, we will do something called hydrolysis. Iron chloride is a strong acid. That does not look anything like an acid. Okay? So we will learn why that is. Sodium phosphate is a strong base. We will learn why that is. Okay? But just looking at them, you would not think those are acids and bases. Okay? So this leads us to the Bronsted-Lowry definition. All right? One was Danish, one was English. They both get credit. An acid is any substance that donates a proton. Okay? So an acid is and by proton, I mean H+. What do you think a base is? That what? That accepts a proton. That's it. If you remember those two definitions, I'm not going to say you're going to get everything right, but you're on the road to figuring out the answers to most questions. Okay? Well, because every question starts with, is this an acid or a base? And then you kind of have to peel off of that. Not every question. But. Okay, so can I flip the page? Oh, yes.
So if you put iron chloride and sodium phosphate into a thing, what do you do?
Well, we're going to get into that. There are strong acids and there are weak acids. Strong acids, you'll see maybe today, but tomorrow for sure, hydrolyze 100% or close to 100%, whereas weak acids don't. And then we have KQs for those acids. I know. We don't call them KQs though. We call them KAs. I told you, KQ is like, it's the whole middle section. The very first, there's no K equilibrium constants. And the very last, when we do redox, there's no equilibrium. Everything in the middle is equilibrium constants. I know. You love it. Okay. Okay. So, because an acid donates a proton and a base accepts a proton, Bronsted-Lowry acids and bases coexist. All right. They exist in pairs. All right. Acids and bases exist in pairs. Because if you have a proton donor, there has to be a proton acceptor. All right. So if we have HCl, okay, HCl plus water, that's the acid. It donates the proton to H2O, leaving us with chlorine all by itself. And because the water picked up a proton, it is now H3O plus. So the water is what? The acid or the base? It's the base because it accepted the proton. So this is the base, and that's the acid. The acid donates a proton, the base accepts a proton. All right, ammonia, NH3, will accept a proton from water, okay, to produce ammonium, the NH4 charged ion, polyatomic ion, and OH minus, a hydroxyl group. So in this case, water is the acid. Okay, so this leads to amphiprotic substances. An amphiprotic substance can act as an acid or a base, depending on the situation. Okay? You should remember that word, right? You can act as an acid or a base. So for example, we have bicarbonate. You know what the bi means in bicarbonate? That's a good guess. So hydrogen carbonate, that name makes sense, right? Bi is the old naming system and it indicates you have a hydrogen. Then they changed it to hydrogen. So it's sodium bicarbonate, NaHCO3, or sodium hydrogen carbonate is the same substance. And that's why if you look in your data package, they have two names, some of them. All right, the old naming and the new naming. Okay, so we got bicarbonate, HCO3. If it acts as an acid, so we're dumping it into water and it acts as an acid. So we got, oh, can't write in highlighter. We have HCO3 minus plus water. It's acting as an acid, so what's it going to do? It's going to give up the proton. So the proton comes flying over here. You don't like I'm just showing this with this arrow thing right now. I'm not going to write that later on. Okay? It bonds to water, so water is now H3O plus. And what are you left with? CO3 negative 2, carbonate ion. And remember the charges have to balance as well, right? What's the charge on this side? -1. What's the charge on this side? -1, positive, and a -2. So -1, they charge. Or they balance. All right. but it can also act as a base. So the base is, we have HCO3 minus, plus we have water. If it acts as a base, it's accepting a proton. So it's going to form, come on. H2CO3 and OH minus. Okay, does that make sense? So because it has, if it has a negative charge here, it can accept a proton. But because it has a proton, it can also donate a proton. That'll change depending on the situation, what it's paired with, which is the stronger acid. If this is a stronger acid than this, whatever this is, in this case it's water, then this will win. But if this is a stronger acid, it will donate to that. But we'll look at that later on. Okay, so it's like a battle going on. Sorry? In this one?
Yeah.
No, this is acting as the base.
Yeah, I know, but is that H2O next to it?
Yes. Oh, sorry. Yeah. That's a bad two. Sorry. There you go. H2O. Okay. Just a bit more definition. If something has multiple protons, such as H2CO3, that means it can donate multiple protons. Okay? And if you can donate multiple protons, you are called, I can't even write, polyprotic. We'll talk about that later. Like, it's easy to get rid of the first proton. It's harder to get rid of the second proton. Okay. All right. Conjugate acid-base pairs. So because we exist with a proton acceptor and a proton donor, and they exist in pairs, we have what are called conjugate acid-base pairs. All right? They differ by one proton. Okay? So if we think about the ammonia one above, I'm just going to write it out. NH. I need a new pen. NH3 plus water. The water will dump the proton. We get ammonium. We get OH minus. So if we look at the the reactants, NH3 plus water, what's acting as the acid? H2O. So it's the acid because it's donated the proton. Therefore, ammonia is the base. But then if we look at the other side, the reverse reaction. So when we're going left to right, water's acting as the acid, dumping the proton. But if you view it, so I said, yeah, left to right. If you view it right to left, going the reverse reaction, the ammonium ion is donating a proton to the hydroxy group, right? So the ammonium is the acid in the reverse reaction. So this is the acid in the reverse. I'll put R there just so we know it's reversed. You wouldn't normally write that, and this is the base in the reverse. Okay, so then we can say that NH3 and NH4 plus are an acid-base pair, or a base-acid pair, I guess. Okay, because this ammonium with a positive charge, it does not want to accept another proton, right? A positively charged ion does not want another positively charged molecule or atom coming near it. It's going to repel it. Okay. I mean, you can. There are things called superacids. We can talk about that later on. That can do some pretty crazy stuff. All right. We do not deal with any superacids. Okay. They wouldn't even let us buy them at school. We don't get to buy anything that's interesting. They don't want us playing with anything fun. I can tell you a story about me evacuating a school and hazmat coming once. So, anyway, okay. So acid-base pairs. Also, the water and the OH are an acid-base pair, right? Because they differ by one proton. So OH minus, all right, is the conjugate base of H2O, right? H2O is the acid. The conjugate base is OH minus. Differs by one proton, all right? And H2O is the conjugate acid of OH minus. Every acid has a conjugate base, and every base has a conjugate acid. Okay? Yes.
Is the conjugate base and acid the same for like every question, or does it like depend on the question? Does this make sense? Like
It
if there was like an H3O,
yeah.
like does it depend on the question? Like if is H2O always the acid?
No. Okay, sorry, that's what you're saying. No. It's going to depend on what you're putting.
Depends on what other stuff
Yeah.
is in the equation.
Exactly. So if water is mixed with a base, water will act as an acid. But if water is mixed with a strong acid, it'll act as the base.
It's not like you just remember which one.
No, you have to look at the equation. But we'll learn how to like which is the stronger acid. That's what I think Kira was asking me. If you have like if you have HA plus HB. All right. Say HB is a stronger acid. It'll dump its proton onto that. So you get H2A plus B minus, like that. Does that make sense? So then this is the base. There's its conjugate acid. But if HA was a stronger acid, it would dump the proton onto HB. So it's a battle between which is the stronger acid. Does that make sense? So I guess every type of question is independent. Water can do both. Okay, I would like you to answer those questions in there, please. And I will post the key in the classroom.